talk about implementing total order broadcast. So before we proceed, the first thing to notice is that it is actually impossible to implement total order or atomic broadcast in an asynchronous system with process failures, or as we have referred to it, fail-silent system. And it is important that you understand why. So feel free to pause the video for a few moments and think about it. So the reason is as follows. So first, consensus can actually be implemented on top of total order broadcast. And we discussed how to do this in the very first lecture of this class. So if you don't remember, then please feel free to revisit the lecture 1's material and you will find the answer there. Okay, but given that consensus can be implemented on top of total order broadcast, so if we have total order broadcast implemented in a fail-silent model, then we can apply the scheme that was used to implement consensus on top of total order broadcast to implement consensus in fail-silent model. But that is impossible because of this FLP result that we discussed 2 lectures back. So basically consensus is impossible in a fail-silent model or equivalently a synchronous system model with failures. Okay, so due to this reasoning, this simple reasoning, we have that total order broadcast is impossible to implement in a fully asynchronous system. So our approach for implementing total order broadcast will be to implement it on top of consensus. Okay, and in doing so, we will effectively package all the environment assumptions that we need to make in order to circumvent the impossibility result that we've just discussed into the consensus module. So these environment assumptions, to remind you, can be failure detectors and or synchrony assumptions such as full synchrony or partial synchrony. So this way, whenever the consensus is possible to implement, and we know that consensus is possible to implement in a fully synchronous model, fail-stop model, or a model with failure detectors, like a fail-noisy model, total order broadcast is also possible to implement. And so we don't need to make any extra environment assumptions for implementing total order if we have consensus given. Okay, and that greatly simplifies the design of the solution. And in fact, that's the approach being taken by virtually all existing practical implementations of total order. And those include Apache Zookeeper, Raft, BFT Smart, Bitcoin, Ethereum, Hyperledger, and so on and so forth. Okay, so we will show an algorithm that demonstrates the core idea how that could be done, meaning implementing total order broadcast on top of consensus. However, keep in mind that our implementation is definitely not the most efficient one. Practical implementations are more efficient, and we will very briefly discuss how they achieve efficiency. However, they all are based on this basic idea of implementing total order on top of consensus. So let's now discuss total order broadcast more precisely. So we have a module called total order broadcast, and its instance is TOB. And we have the 2 types requests that you're already familiar with from the discussion of reliable broadcast or causal and FIFO broadcast, which are a broadcast request to send the message M to all processes, and the indication event deliver, which notifies the local instance of a delivery of message M from process SRC. And The properties of total order broadcast are as follows, so from TOB1 to TOB5. So they are listed on this slide here. So the first property is validity, and it is exactly the same as the validity property of reliable broadcast. So if a correct process P broadcasts a message, then P itself eventually delivers this message. No duplication is exactly the same as the respective property of reliable broadcast. No message is delivered more than once. No creation is again the same as the respective property of reliable broadcast. If a process delivers a message M with sender S, then M was previously broadcast by process S. The fourth property is agreement. So this is what we required from non-uniform reliable broadcast, and it says that if a message M is delivered by some correct process, then M is eventually delivered by every correct process. So the most interesting property is property 5, which is total order, and this captures our intuitive notion of what total order delivery means. So here we are looking at a pair of messages, M1 and M2, and two processes P and Q, which are assumed to be correct for this definition, who deliver both M1 and M2. And what we want is that if one of them, say P, delivers M1 before M2, then the other one, Q, also delivers these two messages in the same order. So it delivers M1 before M2. So likewise, we can also define a uniform version of total order broadcast, UTOB, which supports the properties UTOB1 to UTOB5. So the first three properties are exactly the same as the properties of total order broadcast or reliable broadcast. And then the fourth property is uniform agreement, which is the same as the respective property of uniform reliable broadcast. And it says that if a message M is delivered by some process, which can be either correct or faulty, then M is eventually delivered by all correct processes. And then the uniform total order is exactly the same as normal non-uniform total order that we just discussed, but in contrast to total order, it requires that if M1 and M2 are delivered by any two processes, so they can be either correct or faulty, then if one of these two processes delivers M1 before M2, then the other one does the same as well. That is, delivers M1 before M2.